Hello, good evening. Can you hear me and can you see my screen? Can you hear me and can you see my screen? Visible. So audible also, I believe. Okay. Let me wait for a couple of minutes. 5 past 7, we will start. Let others join. I'm hoping some more people to join. Then we will start. Okay, so it's 5 past 7 already. We will start. Let others join. Mm, yeah, I'm audible, I believe. Once again. So just confirm once again that I'm audible. We'll start. So this is the okay. Thank you. This is the fourth week of this course, that is Electric Machines 2. Um, the course is conducted from IIT Kharagpur. The instructor is Professor Tapas Kumar Bhattacharya, and three doubt clearing or problem solving sessions per week are conducted. I take this session every Monday, 7 to 9 p.m. I am Shaptur Shide. I am a PhD scholar at the Department of Electrical Engineering, IIT Bombay, and I am working on machine design for my PhD. So, before in the last few weeks, we have seen lessons on self and mutual inductances, electromagnetic energy conversion, and last week we started distributed winding. Mostly we studied about EMF generation in distributed winding and various factors, distribution factor, pitch factors in distributed winding that affects the voltage generation, EMF generation in the distributed winding. In this class today, we will mostly focus on this thing. This is called winding table. Winding table. How to make an winding table, how to use an winding table, that we learn from this. So this class is most about how winding is done in a three-phase machine. How is distributed winding done? Okay. So before we start, as usual, I would ask you to ask questions from this week or previous week's lecture. As a reiteration, these classes are doubt clearing or problem solving classes, not actual classes or substitutes of the actual classes taken by the professor. You are supposed to watch those videos, try to solve problems from where if you have some doubt, you are supposed to come and ask in these classes. So over to you. If you have any question from this week or previous week, you can ask. I will wait for some time. Have you watched the videos? Okay. Okay, then we'll start. Now, this is about distributed winding. So, right. Distributed winding. Now, there are several terminologies regarding distributed winding, which make it easier to understand one winding. One we saw in the last class, that is slot per pole per pitch. Second is something that we call layer, that also we saw, double layer, single layer windings. And there is something called throw, coil throw, also short pitching and all we have seen last day. So we will first have a very general idea about how does a distributed winding look, where are the coils put and all, we will see. Now this is something that I'm going to draw. See, machines, most machines except for linear machines, obviously they are round. Linear machines are linear. Now round machines are put in this fashion. These are the teeth, this way, like this. Now when we are studying machines and all, what we do is sometimes what all colors do I have? We make a cut here. We make a cut here. Just a minute. Yeah, we make a cut here. Means not physical cut. We imaginarily make a cut here and lay the machine open. So in that way, it will look something like this. It will look something like this. Okay. So say this is the iron part. If this is the iron part, then this is the tooth and this is the slot. This kind of drawing or this kind of view is called developed view of a machine. Okay, this is easier for easier understanding, easy to understand, easy to do calculations, easy to represent. Right, first thing. So this is called a developed view. Now we are talking about distributed winding. Uh, how is it done? Say double layer winding, if we talk about double layer winding. So suppose one slot is here, that, okay, let me draw several slots. Again, I am drawing a distributed winding, sorry, developed view in this way. Okay, now let us number the slots. If I number the slots maybe in this way, so slot number 1, 2, 3, 4, 5, 6. Now suppose we have a coil throw of 5. That means if one side of a coil goes in slot number 1, it would come back from slot number 6. And this is the overhang. Okay, this is a coil throw. Now how is the winding done? First of all, you cannot simply put winding on this. Some insulating papers are put, however, that doesn't affect our calculation of winding and all. It affects your machine design. When you are calculating how much slot depth you need, there you have to consider all this when you are designing a machine. This you have. So these kind of papers, plastic, not paper, some insulating material are put. Then what is done is a double layer winding, you remember. So two coil side mm, in every slot. So first what is done is the coils are put like this. Say one coil is first made using a bobbin or something. So once you make a coil, the coil looks like this. Sorry. So make a coil. The coil looks like this. So it goes in from here, then several turns, goes around like this, ends and comes out from here. Okay. So several turns are here. Now one such coil, suppose the coil looks something like this. Okay. Something like this. And there are two terminals. Now one such side, say this side, is put here and it is kept vertical. So now the coil is looking something like this. Okay, the coil again here also vertically it is put. Now after all the slots are filled up with coils like this, then what is done is you throw the coil so that this end reaches where it is destined here. I have drawn a long, okay. So let us say coil throw is not 5. Okay, let us say coil throw is 2. So if it goes into 1, should come up from 3. So this you throw, it goes here. So now this one looks like this. Let me remove the arrow. So this one now looks like this because you have thrown it down. Similarly, you throw this, it comes here. You throw it, it goes here. This way, the winding is done. This way. So from one side, you will get to see a picture like this. The say this one coil goes, beneath this another coil goes, Very symmetric pictures. Another coil goes like this. So this is how the end winding looks. So what you get to see from here, if I draw this one once again, suppose you are looking at a machine from the top. This is the ore, the iron, and from here you get to see the end winding. I hope what you know what is end winding. End winding, or sometimes it is also called overhang. So now if you look from here, it looks something like this. Very symmetrical view. Like this it looks. Let me see if I can find a good photo. Photo of end winding, if I can find. Distributed. Okay, something interesting came up here while searching for the photo. This one is good, although schematical. Okay, let me show you this. Not an actual winding. It got blurred. So you see, they are coming up and going in like this. Keep seeing the photo. Let me find out some good. Several photos are here, but not any one of them. Look beautiful. I have seen beautiful end windings in our laboratory at Shibpur. And at that time I was in second year, one professor, um, he just looked at the end winding and told us that it's a 6-pole machine. I was surprised. Professor Sengupta did so. Just looked at the end winding and told that it's a 6-pole machine. Just looking at the color of the insulations. Okay, anyway, that is the best photo I think available. End windings are there, but with insulations I'm not getting. Anyway, this photo you might like. This is a little bit different. Here you do not actually have a lot of turns, very less number of turn. This is called hairpin winding. This thing is now being extensively used. If you later on go for machine design research, you might find this helpful. So hairpin windings are like they have two parallel side, and another one is something like this, bent like this, bent like this. So from the side it would look something like this, so that it instantly go into the slot. As a result, what happens is, if this is the slot, inside the slot the conductors go in like this. Conductors go in like this, instead of the conductors going like this. If you understand, no, if there are round conductors, there will be lot of interconductor space, that you cannot utilize. But if they are square or rectangular, you can utilize more space inside the slot. So from here, one more concept that comes up that we call is SFF. Not directly uh, not directly related to distributed winding, rather true for any winding. So SFF is slot fill factor. More basic is CFF. more basic is CFF, that is copper fill factor. That is the total area of copper you have inside the slot. So area of copper by area of slot. Now area of slot has several things. Firstly, obviously area of copper. Then you have area of insulator of the winding plus area of the insulating paper that I showed, plus this interwinding gap that you cannot avoid. So whenever we are designing the machine, some thumb rule we keep, say short fill factor. If you are going to hand wind the machine with round conductors, some 40 to 45% is the best you can achieve in terms of copper fill factor. Maybe if you go for machine winding, means winding using another machine, there are machines to wind machines that is used for winding, then you can have higher copper fill factor. Okay. Now how thick wire you need here, that depends on uh, how much current you have and what kind of cooling you have. So there comes the concept of current density, that is the RMS current that is going to flow divided by the area of the conductor. Now how much current density to take, I think we discussed it in the very first lecture. Depends on the cooling. If it is if there is no cooling, that is naturally cooled, then we take 5.5 to 6 ampere per millimeter squared. If there is, say, water cooling, not water comes later, natural cooling, then comes forced air cooled, you can go up to 10, water cooling maybe up to 15. In this way, depends on how much and what kind of cooling you are having. Okay, this is how we wind machines. This is how the considerations behind winding goes while winding a machine. Okay, any doubt up to this point? Okay, so we are now going into winding. See, the thing is, three-phase winding might look overwhelming to you, because as a student, means as an undergraduate student, it used to look very overwhelming to me. Like, how do I know where to put which coil and all? So do not look at the whole winding at the very same time. We will try to understand the winding step by step. Okay, that will give us an idea which coil side will go where. Okay, and this will also give you the concept of pole. When you have magnets, it's easy to understand the number of poles. Magnets, or when you have concentrated winding, it's easy to understand the number of poles, because say if you have magnet like this, say if you have, this is the core, and on the core you have magnets like this. So this magnet, the arrow shows the flux direction. So this is clearly a four pole arrangement. You have four magnets simply. So four pole, this kind of arrangement is also called surface permanent magnet type arrangement, and you might have heard these terms, I don't know. You can put the magnets inside also. You can put the magnets inside also. Uh, so this is called IPM, interior permanent magnet. Apparently, like, like I used to think what's the difference. At the end, you have magnets, either on surface or inside, but they are actually different. Lot of difference is there. But at the same time, you can have concentric pole, a concentrated winding also on salient poles. If this is a salient pole, you have windings here. Clearly, this is a four-pole machine. But when you have distributed winding, how to create the poles, number of poles, how to create. Okay. So these all things we will try to understand from today's class. That means the objective is that you don't have to memorize the slot numbers and all. You can yourself find out how to make the winding. Okay. Now let us look at this winding. An incomplete winding table of a 6-pole machine is given below. Okay, you observe this for a minute. What you have to observe is you count the number of coils that we have per phase, and then try to find out the number of slots. I'll just prepare another device by then. This is a distributed winding. First of all, you tell me whether this is a single layer winding or a double layer winding. Looking at the numbers, can you guess? Observe carefully the numbers. Or maybe other notations with numbers. Can you guess? See one thing. Just look at these numbers. Maybe the left hand side numbers, they are not primed. It's 1, 2, 3, 4, 5, 6 like this. Whereas the right hand side numbers, they're primed. Or you can say in this fashion also. Look at this. Here we have 6 prime, here we have 6. Although this is incomplete, but we are not going to see more than double layer in this level or something. So definitely this is a double layer winding, because number 6 slot is definitely having two coil sides. The return side of coil 1 suggested from here, and the going side, sorry, not coil 1, or we can call it coil 1. Let us call this coil 1. And the going side of coil 6. These two coil sides are there in slot number 6. So clearly, this indicates that this is a double layer winding. Understood? This is definitely a double layer winding. So this is the first information that we can extract out of this, that it's a double layer winding. Okay, some more things are given. So what you have to find out is number of slots. How many slots are there? Now that we know that this is a double layer winding, last day we discussed. Okay, there was something in the chat. Double layer winding. Village said. Okay. Last day we saw that, or we discussed that for a double layer winding, number of slots equals number of coils. So how would I know the number of slots? Just count the number of coils. If you quickly count the number of coils, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 12 into 3, 36. So it's a 36 slot. So what we get is 36 slot, 6 pole. 6 pole they have mentioned here. 6 pole machine. This much we can find out. Okay, 36 slots, 6 pole. Let us see what else we can extract from the data. 6 pole, 36 slots. So now if I look at one pole pair span, we discussed this last day that one pole pair or a 2 pole machine is the smallest possible machine that you can have, unit machine. One pole pair, if we have, so total 3 pole pairs we have, out of which we have taken 1 pole pair. So 1/3 we have taken. So definitely there will be a total of 12 slots. So 12 slots will make one pole pair. So if I have, say, slot number, so slot number 1, 2, 3, 4, 5, 6 here, 7, 8, 9, 10, 11, 12. Okay. Last day we discussed that two sides of a coil will be under two different poles. So if the going side is under north pole, the return side should be under south pole. Then only we can have additive EMF in the two coil sides, and we get a total positive EMF. Basic DC machine concept. Okay. The EMF generation is nothing different in be it a distributed or concentrated or whatever. It's Faraday's law. So if it is a full pitch winding and one coil goes at slot number 1, it should return at slot number 7, isn't it? Full pitch. So one pole pitch means from here to here, one pole pitch. So full pitch means one, if it goes, say, from the first slot of north pole, if it goes, it returns from the first slot of south pole, 7. So this coil under full pitch should look like this, 7 prime. That means the coil was first made like this, then it was thrown to, say, slot 7. But you see here, it is 1 and 6 prime. It is not 7 prime, it is 6 prime. So what does that suggest? What does that suggest? It was supposed to come back at slot number 7. Rather, it doesn't come back at slot number 7. It does not complete a full pitch. It is short pitched. So it's a short pitch winding, not a full pitch winding. short pitch winding. Okay. Now, how much is a short cording? One short corded by one slot. It was supposed to come back at 7, it comes back at 6. Short corded by one slot. Clear up to this? Okay, so short corded by one slot. So from now we can say that any coil will look like this in this machine. Any coil will look like this. Understood? Right. Now, so we'll find out one more thing. This is very important. In fact, you should have done this before doing this short pitching and all. This gives a very clear idea about how the winding is going to look like. That is SPP, slot per pole per phase, 36 slots, 6 pole, 3 phase, 2. The 2 slots per pole per phase. Okay. Let us do one thing. Let us draw the whole thing so that things become more clear. Let me draw the slots. So how many slots I have to draw? Let me draw 12 slots. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay. 12 slots I have drawn. Let me write 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 slots are there. Okay. Now we have seen here that 6 slots will create one pole. So let us say from here until here is North Pole, and then there it is. So this is one pole. This much is one pole. Now look at this SPP. Slot per pole per phase is 2. So out of these 6 slots, 2 will be occupied by one phase. So phase A. Let us see here. The phase A winding is completely given. So let us see how many numbers we have between 1 and 6. 4. We should be expecting 4 numbers. Why 4 numbers? Because 2 slots and double layers. So 4. So 1, 2, 7, 8. Sorry, not 8, not 7, 8. 1, 2 within 6. 1, 2, 6 primed, and okay, there is one unknown. There is one unknown here. So let us do this. We did this in the last class. If this is 32, then by this logic, this should be 37. but there are only 36 slots, so 37 is actually 1. So this W prime is actually 1 primed. So what do we have? 1 primed. Let us see what do we have from this table. I'm finding out 1 2 6 primed, 1 primed. 1 2 6 primed, 1 primed. So this all we have. So no, wait, there is something, a little bit of change we have to do here. This is short corded. So what we have at 6 should actually be at 7. So we cannot consider 6 also. Is there 5 somewhere? Or is there 36? Actually, we have to consider this one. We have to consider this one, these two. See, had it not been short corded, this coil number 31 that returns at 36 would have returned at 1. Okay. Anyway, so what we have is 1 2 6 and 1. So if I now draw 1 prime, do we have? So let us say it's like this: 1 prime do we have, and 2 we have. Let me do the other way around. Let me say this is going, this is coming, return. The go, cross is go, dot is return. So 1 primed, 2 return, and 6 here, like this. Let me also draw some more slots in this direction. That will be easier for visualization. We can just look at it and draw the other phases. Draw. So what do we have at 36? 36 primed. 36 primed we have. Look nice? Yes. Now you do one thing. I would ask you to look here. You concentrate here. Let me change this pen. Yeah. You concentrate here. See, the coils of one phase, they are at one place. In between, from here to here, the phase does not appear. This color is purple, not visible very well. From here to here, these coils do not appear at all. From here again, this phase appears, but in the other way around. So now, without even looking at the winding table, just by looking at this encircled drawing, we can draw the other side of phase A. Only thing, oh sorry, this will be dot. So this just a minute. If it is 1 primed here, (36) was prime. So dot. Okay, let us go ahead. Just by looking at it, we can draw the other side of the pole. Now, this is how you make one pole out of one phase, one pole pair. So this is one pole, this makes one pole, this makes another pole, and they keep on repeating. Can you understand that the next phase would also appear in this fashion? Now, if I draw the next phase, this will also look like this. Here and here. Phase A, phase B, and if I draw another, let me take a lighter color. If I draw another, just look at the repeating pattern color wise. Can you find out the symmetry? Can you find out the symmetry? This is how we make poles out of the winding. This is how we make poles out of the winding. Now, understand one thing here. These dot and cross do not show you the direction of current, because you can consider whatever is moving, pole is moving or winding is moving, whatever. If you have a given pole, say a north pole here, and this is moving, it cannot happen that some windings are having current towards us, some windings or some coil sides are having current away from us. All of them are carrying current in the same direction. This dot and cross, they show the direction of winding, or the direction the coils were wound. Okay. Okay, only the whether it is. Now let us see if it is matching. See, this part of the A winding, we did not draw looking at the winding table. We simply drew it by looking at the pattern. Let us see if it is matches. We should be able to see 7, 7 prime and 8 here. See, 7 is present, 8 is present, 7 prime should be somewhere. 7 prime is here. Right? So this is how windings are made. Now, since they are symmetric, without knowing anything, it is also possible to complete the winding table. How? Just look, observe the numbers. You have 1 here, 1 plus 4, 5 here, 5 plus 4, 9 here. So just keep doing that. So 7, 11 will complete this winding table. Okay. So although it's a very trivial work, simply addition, just keep on adding 4. Okay, so let us look at this, look at the significance of the difference. I think you can all find out. Make sure that you complete the winding table. In exams, question might appear like this. Like for example, we had W here. So W, X, Y, Z, we have to find out the values of W, X, Y, Z. So simply we'll only find out these 4 variables. You can complete just by adding 4 and all. So 19, so 19, this will be 23 clearly, and say 25, this becomes 29, 29 plus 4, 32, and 32 plus 5, 30. Hey, 29 plus 4 is 33. 33. 33 plus 5 is 38. 36 slot machine. So 2. Clear? 5. 33 plus 5 is 38. 36 slot machine. So 38 cannot be a slot number. So 38 minus 36, 2. Similarly, 32 plus 5, sorry, 32 plus 4, 36, 36 plus 4 is 4, and 4 plus 5 is 9. Z should be 9. Tell me if there is a doubt here. Okay. Now we could do this so easily because these numbers, some numbers in the B phase and C phase were given to us. Suppose you are given only some numbers in the A phase. Say numbers of A phase are given. No number in the B and C phase are given. Can you find out this number 5? Can suppose this is unknown to us. Let us look at it. Thing is, see, we have used 3 colors here. We have used 3 colors here to draw the windings. One is this one. This one we have used. Another one is this one for another phase, and the other one is this one for the third phase. In this way. Now it's up to you what you name them. You name them anything. Say if I name this one A, you can name this one B, the other one C also. What they have done is actually, this is why they have given some numbers of the other phase so that you cannot, so that means one can take red one as B, or other, someone can take the light green one, blue one as B. So what they have done is taken the blue one as B. How do I know? You see, we have kind of winding pattern. We have a winding pattern that kind of looks like this. One pole looks like this, isn't it? Just from here, you see. I won't leave this diagram dirty, so I will remove this. From here, we have winding pattern. One pole of a phase looks like this. So this thing keeps repeating. So see, you see, for the blue, light blue thing, it's repeated here, right? Now, what is 1 for phase A? What is 1 for phase A? 1 is in this position, this one. So for phase B also, it should be for the other, forget phase B, for the other two, if this is this one, it should be this one. Next phase, And if it is this, so deep blue, light blue, then comes red, this one. So 159 we have in the winding table. There should be a 3 somewhere. If there is 3, let us find out where is 3 in this winding table. 3 means 39, 35, 31, 31. This one. So 31, 35, 3. So it's all about how you how you make the table. The question that could have come here that I was thinking for some time, why not I say after this I will take slot 3, then I will take slot 5. That is also possible. In that case it would look like 1, 3, 5. It would look 1 here, 3 here, 5 here. See, that is also possible. In that case, just the phase gets interchanged. 3 is actually in phase C. We rename it as phase B, and the other one goes to phase C. B gets renamed as phase. That is also possible. Winding table, winding table. Now look at this diagram carefully and observe this. This is very important to have a feeling. So I was telling you that one professor, he looked at the winding and told it's a 6-phase machine. How could he do that? The red phase, phase A winding, they were insulated by red colored insulators. The coils had a red color covering, and the blue and the next one had a blue color covering, and the next one had a green color covering. He simply looked at the repetition. He simply looked at the repetition. How many periods are there? He saw that there are 6 periods. Hence, it became a 6 pole machine. I don't know what was his thought process, but I think that is the way. Just looking at it, he could say that. Here also, you see this thing. So suppose you are not said anything. Simply this diagram is put in front of you. You just find out a pattern. Say in this case, this is the pattern, and how many times it repeats itself for one phase. So that many poles are there. Okay. So is the winding understood? So whenever you are doing a solving problems on winding, instead of directly jumping to this, to try to do all these things, try to extract as much information as you can from it. It is a good learning process, and when you are done doing everything, you have all possible information at your hand. So I hope things are clear. Okay, then we will start solving these things. Now we have everything, we have to simply calculate. First question is coil span. So we saw coils were like this. N2 N plus 5. So coil span in electrical degrees. So there are total total is 360 degree. Now when I am saying total machine is 360 degree, obviously it is mechanical. 36. So this is slot pitch in mechanical degrees. Now coil span is 5 slots, so into 5, still in mechanical. So we have theta electrical equals P by 2 theta mechanical. So multiply with 3. Number of pole is 6. 3. So whatever you get, 150 degree electrical. 360, 10, 5, 5, 25, 6, 150 here. If you have understood the discussions we had so far, this is very well understandable. Okay. All right. So the next one is pitch factor for third harmonic. Pitch factor that we saw for nth harmonic, it is cos n sigma by 2, where sigma is a short chording angle. Short chording angle in electrical degrees. So third harmonic they have asked for 3 by 3. These 2 comes here. Short chording angle in this case is 1 slot. So 360 degree by 36 times 6 by 2 to make it electrical. To make it electrical. Can you find out? What it should be? This becomes 10, becomes 5, this is 3, cos 45 degree 1 by root 2. What is 1 by root 2? Let me just 1 by 1.44. Okay, I think I'm not making a mistake here. Yeah. Okay. So the next question is phase spread. What is phase spread? What is phase spread? How much of phase spreads? I think under so under one pole. It has to be under one pole because otherwise it will keep changing from machine to machine. Means it will always change from machine to machine, but it will keep changing with number of poles even for the same winding distribution. Can you understand that keeping the same winding distribution, you can keep on multiplying this distribution to have more and more number of poles. Just keep the pattern same, then keep the pattern same, and then keep repeating the pattern. If we whatever you have, if you do it twice, you get a 12 pole machine, but the properties remain the same. The winding properties remain the same, because all the calculations we do are per pole. So phase spread per pole, we had, how much do we have? We have 2 slots per pole for each phase. 2 slots. You can say like this, here to here. Or maybe it occupies 2 slots. No, that is different. Spread is like this, 2 slots. So phase spread is 2 slots. 2 slots in electrical degrees, it will be 360 by 36 into 2 in mechanical into 6 by 2 in electrical. So 60 degree. Right? Phase spread becomes 60 degree. Distribution factor for third harmonic. Let us do one thing. Let us quickly find out. Okay, anyway, later we'll do. Distribution factor for third harmonic. We found out last day that it is sine what was it? Just a second. It's for third harmonic. So n times SPP times beta by 2 divided by sine. SPP comes out. N beta by 2. N is the harmonic component. In this case, n is 3. So what do we have? Sine beta is unknown to us. N is 3 because third harmonic. Slot per pole per phase we saw 2. Beta I am writing. Again, beta we have to write in electrical. SPP 2 sine 3 into this by 2. Okay, what is beta? Beta, if you remember this diagram, why did this distribution factor appears? Because our EMFs do not get add up like this. They do not get add up like this, rather they get add up like this. It should be all equal in length. And what we finally get is this. This angle is beta. So here is one coil of a phase, here is another coil of a phase. So how much is a phase shift between them? Phase shift is 1 slot. 1 slot means, so phase shift is 1 slot. 1 slot means 360 by 36. In electrical degrees, this much. 30. So beta is 30 degree. So you put 30 in 30. Sine 90 is 1. Sine 45 is 1 by root 2. So 1 by root 2. Understood? Why I got this value of beta? Okay. I think I'm audible. I'm not getting a single sound from your side. Am I audible? Someone could please confirm. Just write in the chat at least. I should be audible. Okay. Okay, so it's understood, I believe, up to this. If not, you can always ask me questions. Next question is, what are the values of W, X, Y, Z? We have already done. W is 1, X is 23, Y 2, Z 9. 1, 23, 2, 9. We have done already. Just write it here for reference. 1, 23, 2. Okay. Now we find out the voltage. Each coil can carry at most 5 ampere current. Hey, how can they say it can carry at most 5 ampere current? What decide this? We just discussed. Two things decide this. One is the thickness or area of copper, better to say, how much they have kept, area of copper. And other one is what kind of cooling they have considered while designing the machine. Okay. So each coil can carry at most 5 ampere current. How much is the maximum amount of phase current this machine can supply if the coil groups are connected appropriately? Okay. So question is, how much is the maximum amount of phase current? Now see, you have several coils. Okay. Several coils. All of them can conduct a maximum of 5 ampere. You have to make sure that the most possible current you can get. So what you have to do is you have to correct them in parallel. Then only all the current add up, and you get like this. Understandable, no? Forget coil. Since we have been told that they can carry at most 5 ampere, let us consider them as current sources of equal currents, all of them 5 ampere. Now you want the maximum current out of it. What would you do? You would parallel them. You would parallel them. Then only you get the maximum possible current, which is summation of all the currents. Since they are of equal values of current, you can have them in series also. Unequal current sources you cannot connect in series. Unequal voltage sources you cannot connect in parallel. I'll try to have this current source voltage source discussion sometime in this course. Very interesting. Okay, so now each coil can carry at most 5 ampere. How much is the maximum amount of phase current that is machine can supply if coil groups are connected appropriately? This machine, they have said. No, there is something missing here. Star or delta, they have not mentioned. The current will change on that. Let me think a little bit. You guys can also suggest if you have something in your mind. Just thinking how the connection should be. There are several ways of doing connection here. They are saying each coil can carry at most 5 ampere. Now, A phase has 12 coils. But there is a catch here. You cannot simply say that if that is 12, then it should be 5 into 12. 60. This cannot be said because these currents are not DC currents. They are shifted. They are AC currents and they are shifted in phase. How it should be then? Any idea? The way it is being taught in the class means the convention that is being followed in the class. By that convention, I think that is the convention you have to follow in the exam also. That would depend on the coil groups that you have, groups per phase. So it is like this. Say every phase per pole looks like this. These two make one group. These two make one group. You see, 1 and 2 makes one group. That's why they are in this color. A little bit of shading difference if you can observe on the screen, I don't know. So this is one group. Let me this is one group. So 1, 2, 3, 4, 5, 6. 6 groups are there. So basically, let me then draw it in a better way. The way this kind of drawings you will also see sometime in places. I don't know, maybe it has been showed in the class also. In this vertical fashion, it is shown sometime. But unless the connections are shown, so say slot number 1, slot number 6. slot number 7, slot number 2, 1, 2. Now connections are shown like this. One wire will be here, 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 and here. So these show the respective. These show the respective. What to say? Respective coil ends, and so these coils, the winding starts like this, goes from here, winding is complete, comes out, and the connection goes here. Comes, so it was, so can you understand? Winding starts from 1, say there are 100 turns, so it rotates in this way. Rotates means it's wound in this way 100 times. It goes like this, rotates like this 100 times, like this. Once this is complete, sorry, I drew it wrong. It rotates like, yeah, this 100 times. Once it is over, 100 turns are over, it comes out. Then the coil 2 winding starts, next winding starts. This way the winding is done. And here coil grouping, each group has 2 coils. This way. So this is one unit, what they are saying, according to their convention that they are following in the class. But still, this is not very, there are several possibilities here. So this is one coil, that is a coil group is wound like this, and you have 6 such, you have 6 such. So the maximum that you can have is not this. Maximum that you can have is 5 into 6, 30 ampere, but this is still not correct. Or is it correct? No, it is correct. Why? Because all the groups are always seeing the same magnetic field. Yes, this is correct. And each are carrying 5 ampere. They are in series, so they have to carry the same current. Can you understand? All the same groups. Look at this group. Let me look at this group. This group and this group, they are placed at magnetically equivalent scenario. One under north, one under south, that's a different thing. But the magnitude that they are seeing are same. So the currents flowing through them are equal because they are in series and are in phase. That's why you can simply add them arithmetically. It's 30 ampere. You see, if there is a doubt, I think I missed one question that I will quickly bring on the screen. Because without the EMF, you cannot find out the kVA. Is it understood? So we put them in parallel so as to have maximum current. Have maximum current. Now, 2 coils of one group that are now highlighted in green, they are connected in series, though the current through them has to be the same. but the voltages will be different. Why? Because if you see, we had this discussion once while discussing um, distribution factor, because I'll erase this, because this and this, they are seeing different values of magnetic field. If this is the magnetic field, magnetic flux density distribution, one coil is placed here, the next one is placed here. This is where the distribution factor comes into play. For the current, we can say they are same because they're in series, but for the voltage, if we have to find out, we cannot simply say two coils in series, so 2 into 50 volt each. 1 kd will come, distribution factor will come. And 1 kp will come, pitch factor will come. Now, since nothing is mentioned, this is definitely what is it called, fundamental. So we'll quickly find out the fundamental kd and kp. These three will be removed simply. So sine 2 into 30 by 2, we did it before for the third harmonic. Now we are doing for fundamental. Someone quickly do it and tell the values. How much was sigma? So see, these three will not come, so cos 15 degree. Tell me the values quickly. Are you doing? I hope you sit with calculators for this class. Sine 30 by 2 times sine 15. Why would that take this long? For some reason, they are coming the same. I don't know. So this is what you get from this group. These groups are series connected. These two coils in a group, they're series connected. They are connected in series. That's why we can say the same current is flowing 5 ampere. They are connected in series but shifted in space. Why shifted? Because you cannot have both of them in the same slot. Shifted in space. Now since they're shifted in space, this KD appears and KP appears because they are short corded. Two coils, so you can say two AC voltage sources in series. They are equal in magnitude, but there is a phase difference. Who takes care of this phase difference? KD takes care of this phase difference. See, we are solving everything from the first principle, either Faraday's law or this simply phasor addition or everything. There's nothing special here. Only thing is you keep deriving, then some at the end you have some theory. There you do not do everything from basic. What you derived, those things you use, but do not forget how you derived. At least the origins you do not forget. That KD came from phase difference actually. Okay, so this is what we get from one phase group. Now there are 6 phase groups. Question is, how much is the maximum phase voltage we can have? Again, phase groups are under similar magnetic situation. Under Kavilash answered. Under similar magnetic situations. So they will be in phase. They will be in phase. And if you want to have maximum voltage sources, you have to connect in series. So these many groups per phase, 6 groups per phase. So 6 such voltage sources come in series. So the maximum that you can have is what we calculated that times 6. So 93.3 times 6. This much. Now the final question is kVA. kVA. Now you see maximum kVA. We had two problems. We solved two problems. One is maximum current, where we took the groups to be in parallel to get maximum current. Then to get maximum voltage, we put the coil groups in series. Now the machine cannot be having both. They are either parallel or series. So we will do both. First, the coils are parallel. So three-phase kVA. So 3 times for 3-phase. Parallel is the first one when we had 30 ampere of current. Now you connect all the voltage sources in parallel, so voltage remains the same, 93.3. Or if they're in series, then current remains same. All of them give you 5 ampere current. 5 ampere current. So current remains same, but the voltage is this. So you can understand that whatever value you get, it will be same for both. You either multiply the 6 with this one, the current, or so this 30 is just 5 into 6, and this is 93.3 into 6. The same thing you get. Same thing you get. So 90 times 93.3. V. Okay, so that's all the problems we have for today. If you have any doubt, you ask. Okay, I will take a break. If you and I will come back in 5 minutes. So if you have any doubt, you can write in the chat box. Write full sentences in chat box. I will come and answer if there is any doubt. Okay, since there is no question and almost everyone has left, I will call this a day. Next Monday, 7 p.m., we will meet once again and we'll discuss whatever we have. Thank you.